Okay, welcome to our first and highly experimental video lesson. I'd be interested to have your comments, see how it goes. It's obviously not going to be perfect, but any feedback would be appreciated. Now the first session that we're going to do on here is going to be all about work. Now when we talk about work in a physics context, what we really mean is energy. We're talking about the work done moving an object to place, which differentiates it from, say, our physical definition of work that we use every day, where we say that we do work when we're sort of sitting reading a book or writing. Sure, some of those situations are transferring energy, but really in mechanics we're concerned with the movement of objects and the amount of energy we've done moving an object from a place to another place. So let's look at one of the more simple examples first of all. Let's imagine that we have a weightlifter, and he has lifted a set of weights up to a certain height. This guy's quite tall, so he's lifted up his weights quite a long way, say 2 meters. He's a tall guy. Now to do that he's had to apply a force. Now the minimum amount of force he's going to need to get that thing off the floor is going to have to be greater than the weight of the object, which would be given by mg. So the force he's applied to get it up there is going to have to equal mg at the minimum. So the energy transfer here is he's giving it the kinetic energy to get up to that height where it's gained gravitational potential energy. And the formula that you should be familiar with from GCSE, the work done on this object is equal to the force applied multiplied by the distance travelled. Now I'm going to add to this a little bit of an extra, which is in the direction of the force. And that's important. We'll look at some examples of where that's not the case and where it is the case in a moment. But let's be clear about what we mean by work here. We've transferred some energy into the object to give it gravitational potential energy. Now one of the confusing things about work is we might think that we're still doing work when we've got it at that height, in that we'll get tired. This person can't hold the weight forever, so surely they're transferring energy. Well, it's true to say in their muscles on a microscopic level their cells are contracting and relaxing and contracting all the time to keep that weight at the height it is, but it's not doing any work on the object. The weight is staying at the same height, so there is no extra work done on it. So we're going to give ourselves a new page and look at some examples of where this is used. So the first example we're going to look at is almost the reverse of the one we just had. Yeah? In the one we just had, we gave kinetic energy to an object to transfer it to G.P.E. We lifted it up to a certain height. And we'll look at, in a later example, exactly what's going on with the maths there. But now we're going to look at it in reverse. We've got an object being dropped from a cliff. It's got a certain weight, say its weight is mg, and given that its mass is 1 kilogram, then that would give us a weight of, say, 10 newtons approximately, taking g as 10. And say the height of our cliff here is 10 meters. Now in this case the force applied is just the force downwards, and the force downwards is taking it from G.P.E., gravitational potential energy, and it's transferring to kinetic energy at the bottom. So at the bottom all of that G.P.E. will have transferred to kinetic energy. So work is done on the object to get it to a certain velocity. So what is the work done in this case? Well, nice and simply, it's the force applied times by the distance. So the force applied in this case, the work is being done by the weight, so it's 10 newtons times by the distance, which is 10 meters, so we get a work done of 100 joules. Now at this point we'll take a sideline just to remember what the definition of a joule is, because joules are defined by work done. Now the joule, the unit, the joule is in fact the work done when we apply 1 Newton of force over a distance of 1 meter. That is the physical definition of a joule. So that's all very simple. We've seen lots of examples like that, I hope, before. But we'll start to look at situations where we have to apply this thing of the distance travelled in the direction of the force, because it's not always that simple. Let's have a look at another situation involving the ball or the rock. So we might have a situation where we've got a ball at the top of a hill, and the height, as before, is 10 meters. But this time the ball is going to travel down the hill, which is a longer distance, say 50 meters. We've still got the same force of 10 newtons coming from the weight. But what happens in this case in terms of the energy? Because the ball is travelling a longer distance. Well, that may be true, but the direction of the force is downwards, so we only have to consider the distance travelled in the direction of the force. So the only distance travelled in the direction of force here is 10 meters. We don't need to consider the 50 meters at all, because we know the vertical distance, which was parallel to this force line here. So it's the same as before. We use the vertical distance, and it's 10 newtons of force, 10 meters, so the work done again is 100 joules. Okay. Now the next example we're going to look at is a slightly different situation, just to highlight the problems with work done and making sure that work has actually been done by the object. So in this example we're going to have a look at a satellite in orbit. So let's just draw our Earth here, beautiful circle, and our satellite is orbiting around the Earth in a perfectly circular orbit. This is always the same distance from the Earth, even though it doesn't look like it. So that's our satellite orbiting. Now imagine the satellite has a certain weight, again towards the centre of the Earth. It's going to have a weight of mg. So how much work is done, say, getting the satellite from over here to a new location where I'm drawing it sort of with a half sketch here? How much work is done from there to there? Well, what we need to consider is how far is it moved in the direction of the force. Well, at this point here it's still the same distance away from the Earth, and the force is always towards the centre of the Earth, so the movement is always perpendicular to the direction of the force. So no work is actually done. There's no energy transferred to the satellite. It keeps all the kinetic energy it had before and carries on in orbit. So we have to be careful. In this case, the work done, well, we know the force is mg, but the distance was 0, so the work done on that is 0 joules. Now we're going to look at one more example just to try and clear up some misconceptions about work done, and that's pushing a box along the floor. So we have a surface and we got a box and we're pushing along the floor. So let's draw a guy who's pushing it. Now in this situation what we're doing is overcoming the force of friction. So to start with, when we push, we have a force pushing backwards, which is the frictional force, and then we've got our force on the object pushing it forward. Now to overcome the force of friction, our force, say we call it T for thrust, needs to be bigger than the force of friction. And this leads to a bit of a misconception, because sometimes we talk about resultant force, and in this case if T was bigger than F, we'd have a resultant force here. So do we use that for the work done calculation? Well, the answer is no. We need to use the force T over whatever distance it is that we move the object. So say we move it here 5 meters, we would need to use our force of T, whatever that was, to overcome the force of friction, and we need to work out how much work we did transferring over 5 meters. So I'll give you an example here. Say that the force of friction was 10. We'd have to have a minimum of 10 newtons from T to overcome that force of friction. So the work done in moving this box from here to here, if T was 10 newtons, would be work done equals the force 10 newtons times by the distance moved 5 meters, which gives us our 50 joules of energy transferred. So where's that work, where's that energy being transferred to in that example? Well, we haven't given it any extra GPE or any other force like that. We've transferred that energy really into wasted heat. Yeah, the friction of the surface will heat the surfaces between the two, a bit of sound given off as well. So actually, it's a slightly different example. There's still an energy transfer, but the energy has not been transferred into giving it kinetic energy or giving it gravitational energy. It's gone to heat and light, heat and sound. So we're aware of this idea that the force, or rather the distance travelled, needs to be in the direction of the force. So how does this extend itself in situations where we have an angle, a force at an angle? Well, let's consider an example of a box again. But in this case, the box is being dragged by a person using a rope, and the rope is at an angle to the horizontal, say an angle of 30 degrees, and the force is, say, 100 newtons. So in this case, when we drag the box isn't going to move in that direction. The box is going to move along the surface in this direction, and it might move a distance, say, of 10 meters. So what we need to figure out here is what's the work done on the object in this case, because the distance travelled is in this direction, but the force is not in the same direction. Well, I'm sure you figured it out already. What we need is the component of force in the direction that we have travelled. So if we want to find the component of force in this direction, well, we use our vector sum. We're splitting that vector into two vectors, and this vector here would be the force 100 times by the cosine of 30. So the work done in this situation would be the force in the direction that we travelled, which is 100, rather the component of the force in the direction we travelled, 100 cosine 30 times by the direction, the distance we travelled in that direction, 10 meters, which in this case is going to give us 866 joules. So at this point, I think it would be worth you having a go at SAQ5 in chapter 6 of your textbook. So we're going to consider now individual special cases of work done, and the first one we're going to talk about, which we've already mentioned really, but we're going to just formalise it a little bit, is gravitational potential energy. Because you'll quite often see this separated, even though it's just doing work changing into gravitational potential energy, you'll quite often see a separate equation for it, and it talked about as being a special case. So just to clarify what we talked about earlier, let's imagine that we're lifting a box a certain height. We are giving it gravitational potential energy by moving it over a certain distance. Now, to think about what's going on, we have to think about the forces here. So, as we said before, we've got the force gravity, its weight pulling it down, and the minimum force we're going to need to apply to overcome that is going to need to be equal to mg. So we're transferring energy into kinetic energy initially, and that we're giving it enough kinetic energy to get to the top. And I'm going to do a mathematical proof in a later video showing exactly how the numbers work out for that. And we can do, by showing that example, we can work out that the minimum amount of work we're going to need to do getting it to that height, so it's exactly at rest at that height, is, as we said before, the force, because it's just in the same direction as the distance, times by the distance travelled. Now let's try and put this into a form that you might see it with G.P.E., because in this case we talk about this distance here as being the change in height, and that helps us when we come to examples like the inclined slope, things like that before, where we're moving it up, not necessarily in a vertical straight line. So a more sort of specific equation rather is gravitational potential energy is its mass times by g, the gravitational constant, well, not the gravitational constant, gravitational acceleration, times by the change in height, the amount of height it's gained. And that's another equation that you're probably very familiar with from GCSE. So let's illustrate an example of this then, and we're going to take a new page for that, and we're going to talk again about the inclined plane. We're going up a hill, but this time we're doing it in reverse. We're going from here all the way up to the top. Now that distance here might be 50 meters as it was before, but the vertical change in height in this case is going to be 10 meters. Now rather than us say, well, we've got a force up the slope, we're going to push it with a certain amount of force up the slope, and we can work out the amount of the component of the force that's going to be pushing it vertically, and times that by 10. The gravitational potential energy equation makes it a little bit easier for us, because we know that we were overcoming that weight downwards, which is going to be mg. So in this case here, the gravitational potential energy, we just need to consider the change in height and the amount of work done overcoming that weight. So we just use our equation here. The mass, say we had a mass of 1 kilogram, say, times by g, we'll take g as 10 just for the sake of argument here, and we take our distance travelled as 10 meters. So in this case our gravitational potential energy gained is 100 joules. Now obviously that changes a little bit if we had a resistive force, say some friction from the slope. That would need to be considered separately, and we'd have to work out how much energy was transferred from moving it from over the 50 meters in that direction, which would be a slightly different calculation. But on a simple example, there's no friction. When we go from the bottom of something to the top of something, the minimum force we would have needed is the weight, and the amount of change in height that we've taken the object up to is 10 meters. So the gravitational potential energy it's gained is just given by mgh. Okay, so I suspect you know what's coming next, because in GCSE questions, as in A-level questions, this equation, the G.P.E. equation or the work done equation, are both combined very often with the kinetic energy equation. Now you should be quite familiar with this from GCSE. So kinetic energy, Ke is equal to half times mass times velocity squared, half mv squared. That should be very familiar. Units in joules as always with energy. And a very common question is to ask you about when either gravitational potential energy is transferring to kinetic energy or the other way around. So if we just take, for example, a skater in a half pipe, classic example, this guy's skating down here. At the top he's got his maximum gravitational potential energy, and then as he goes down that transfers into kinetic energy. So at about halfway down he's got sort of half and half, and then at the bottom he is going to be moving his fastest at this point. So this point here he's got his maximum kinetic energy. So a very common example might be something along the lines of, if we had the half pipe as being 10 meters tall and the chap here had a mass, say, 60 kilograms, then first of all, how much kinetic energy has he gained when he's got to the bottom? But then quite a common follow-up to that is, what's his speed at the bottom? So what is V at the bottom of the half pipe? Well, let's think about the steps that we have to go through to get to this stage. So firstly, we need to work out what the change in gravitational potential energy is from the bottom to the top. How much work would we need to do as a minimum to get him to the top of the half pipe? Well, that's where our G.P.E. equation comes in. So gravitational potential energy is equal to the mass times G times H. So in this case we have 60. Again, I'm being lazy and using 10. For G, obviously you have to use 9.81 times by the height, which is 10. So in this case we have 6,000 joules of energy stored as gravitational potential energy at the top. So when he gets to the bottom, he's now got none of that gravitational potential energy. All of that, assuming no friction, has been changed into kinetic energy. So we can by rights say that the kinetic energy at the bottom is going to be, I'll just make a note at the bottom, is going to be 6,000 joules as well. And we can make that equivalent to our equation from before, half mv squared. And we're starting to see how we can calculate that v. Because if we rearrange for v, well, firstly, let's take it over here. So we have v squared, we'll rearrange for first. It's going to be 2 times our 6,000 joules divided by the mass. So our v is going to be that, all that square rooted. So 2 times 6,000 divided by the mass, which is 60, square rooted. Okay, so from that our v should equal, so from that our v will equal 14.14 meters per second. Okay, at this point I'm going to recommend that you watch the follow-up videos with the worked examples.